Welcome back, everybody. We are now going to talk about a retrosynthetic analysis, and we're looking at a winter 2018 exam. This portion of the molecule here and here both come from these carbons here, which come from D-ribose. So we're going to have to use that reaction. You don't have to copy this one out. Just say D-ribose becomes furfural in your forward synthesis. And furfural is going to need to become some useful things. But let's deal with that when it comes up. We have a molecule here that has an iodine up here. And iodine is an ortho-para director. But keep in mind, iodine, OP director. But that doesn't limit your thinking process directory. Sorry. Because it had to be at one time NH2, which in turn came from NO2. NO2 is a meta director. So that position can be used to put on ortho-para groups. I had my hand on the screen, sorry. Meta director. Okay. So I can use the iodine to put that group on because it's an ortho-para director, but it would prefer to put a group para. So I'm not even thinking about using the iodine as an ortho-para director because that would lead to some of the product down here. And you would lose a half point minimum. But seeing these groups ortho-para from each other, in this case para, and keeping in mind that's a CH2 group. So is this. They will direct us towards a para product for the next group. If you choose to have this group on first, then your next group's going there. And then a group after that, well, since the para is taken, would go here. So maybe I'm going to choose that approach right now. I like this to be an ortho-para director, and then I'll be putting this group on, and then I'll be putting the ortho group on last. If I went from this position here, I could still work it. It's another strategy. This is an ortho-para director. It itself will put a group para, that group. But how do you get an iodine meta? Well, you realize this group here, because it's a primary carbon group, used to be a carbonyl. So another note here. This is all in our thinking stages here. That's CH2. We don't know how to put primary groups on benzene directly, but we know how to put carbonyl groups on directly, and that's a meta director. So that's an OP, and that's an M. So I can work this particular example using any of those groups as my starting group. And I confess, I approached these from the forward synthesis direction myself, and then I pretend it was a retrosynthetic analysis question. I know a competent organic chemist wouldn't admit that, but I'm a teacher too, and I realize that you're learning stuff not at an advanced level, but at an introductory level. So, you know, here I'll do my forward synthesis down here, going back towards my target. Here's your benzene. And you also have your D-ribose. So put your forward reactions down. We don't have a group to put on benzene yet. We'll work on that. I'll even go with putting this group on first. So just remember, I want to get this group onto benzene first. That's my strategy because I picked it. And D-ribose upon sulfuric acid treatment. It's a catalyst for the dehydration and cyclization of D-ribose. Quite a fascinating sequence of events to make furfural. And we'll even draw furfural. It's got the furan group on it and an aldehyde, which I'll put right there. CHO. Well, we got to extend CHO for this one. We have to extend it by a carbon. Okay. So let's do that. We know how to make it one carbon longer. Let's see. I can make, well, how do I make one? Well, you could add a nucleophile there, but the carbon you're adding will be like a methyl group. And I don't need the functionality over here. I don't need it there for putting groups on benzene. I need it on the end. So what I'm going to do is reduce this and then make it into an organolithium. And then back in test one, we learned how to extend that. We can put a formaldehyde Grignard reaction in there or organolithium. So a lot of talk, let's just do it. You can reduce aldehydes or ketones with sodium borohydride. And now you've got an alcohol there. And this ring's getting tiresome to draw. Although, you know, it's a cool ring. Let's find a place to circle it and just call it R. So you're going to have your R ring attached to CH2OH. And then I'm going to hit that with PBr3. And then I want to make an organolithium. You can combine stuff here. This is fine. Lithium and hexane. And what we have here is our lithium. We can now make it one carbon longer by reacting it with formaldehyde. H2C00 in step 1. Step 2, HCl. And we have our CH2, CH2OH. And now how can I put a carbonyl on benzene? Because that's what we have to do first. If you try to make this into the old organic bromide and then put this group on benzene directly, thinking you're going to get this result, you're going to be in for a shock when you get your test back. Because what's going to happen, you can make this into a bromide, but as soon as you treat it with aluminum chloride for the Friedel-Crafts alkylation, it's going to rearrange to the much more stable benzylic equivalent, because this is an aromatic ring down here, and I'll make a cation there, and that is not where you want the cation. So people, on your test, you will have to put at least one primary R group on benzene. To do so, you must first put a carbonyl on benzene and then reduce it to CH2. It's going to happen. So here's the protocol. I have to make this into an acid halide. This is 2 steps away from an acid halide. It has the wrong oxidation state. Fix that first. Oxidize it to a carboxylic acid. Remember, acid halides have the same oxidation state as carboxylic acids. They're called carboxylic acid derivatives for a reason. And that's it. And 2, acid halide time SOCl2 and pyridine. And what we have going on now is you have your ring, your R, and CH2C double O Cl. We can put that group on benzene, which is what we're going to do right now. In fact, there's benzene. Did it have to be over there? Do we even have to pretend we're doing retro first, even though we're doing synthesis first? No, we don't. Let's just say I'm going to react that with benzene right now. Benzene. And you need the catalyst aluminum chloride to put a carbon group on the benzene. And now you've got your first group on the benzene. Yeah, let's do it. Sure. And your group looks like this. We'll go back to our target. Let's take a look outwards a bit. There we go. We've got a carbonyl here, and then CH2, and then R. That's what we have. It's a meta director. Let's focus on putting the next group on, meta. And remember, to put an iodine on involves the protocol. Nitration to put an NO2 group on. Reduction of the nitro, NO2 to the NH2. NO2 to the NH2. That's a reduction. And then diazotization to make an N-triple-N diazonium ion. And then iodination using Ki. So quite a bit of stuff to get that I on there. Let's work on it. Step 1, nitration. You can group them together. This nitro group will go meta to the carbonyl. Generally requires heat. I don't usually grade heat. To get the chemicals, I'm pretty happy. 2, reduce that without reducing your carbonyl. We can use the H2 nickel combination. That's going to reduce your NO2 to an NH2. And why don't we write down the product now? Not have too many steps in a row. Still have our carbonyl. Now we have an NH2. Now, if you want to go and try to put the third group on now, you'd have a lot of trouble. Well, you wouldn't be going towards this molecule. If you wanted to go with this molecule, where's the next group going to go? I'll tell you, it's going to go right here because this is a powerful ortho-para director. You can ignore this group when you have a powerful ortho-para director. And the next group goes here, which is clearly not where I want it. You have to make this an iodine. Then you have to reduce this to a CH2. And then the question is, which one of those is a more powerful director? And the alkyl group with its hyperconjugation abilities, a CH2, will dictate over an iodine here that the next group goes here, which is clearly what I want. We'll work on the next group shortly. Okay. So it's time to diazetize and then convert it to an iodine. Diazetization is big on your tests. I can't say it enough times. And don't confuse this with nitration. This is a different oxidation state of nitrogen, NaNO2. I'm going to grade every single piece of this answer. You can't skip the temperature either. These species are unstable above 0 degrees Celsius. Show me you know that. And you're going to warm it up to room temperature in the presence of Ki. There's your room temperature. That short form is common. You don't have to explain it. And you have successfully converted your molecule to this. You have an iodine up there now. You have a carbonyl down here. Now, the next, if you put a third group on, now you have another problem. This is a more powerful director than this meta-directing carbonyl. Your next group would go down here still. I want this to be the more powerful director, and I need to reduce it all the way to a CH2. This is the one reason we learned the Wolff-Kishner reaction and the Clemmensen reactions on our first test. I like the Clemmensen. It involves a lot less writing. It's a mercury, zinc alloy called a zinc amalgam. And, well, I think there we go. And it has to have HCl as well. And 2. Oh, by the way, if you do what I did by mistake and you had mercury first and zinc in parentheses, I don't mind. It all depends on which one's the major component and which one's minor in the alloy. But I don't want to get into that. Okay, and now you've created your CH2. Well, let's just do that. It's critical, so let's just not split it up. And now you've got a new group on the benzene that is a more powerful director. I keep saying that. If we don't know that table with the directors on it in the textbook, the most important table in chapter 22, then we shouldn't even be watching this video yet. Yeah, an alkyl group is a more powerful director than a halogen. So the next group that goes on will be dictated by this group, an ortho-para director, para being major over here. You will get a substantial amount of ortho and ortho here. Not very much there because it's between the two groups. Iodine is big, so I wouldn't be surprised if you get close to 50-50 yield of here and here, but that's the best we can do with our chosen path here. And I want to put the group on. I don't have anything for that group yet, though. It has to be a CH2 that has an O. Wonder how to do that. You've got options here. You've got lots of options. Now, one of my favorite options, I've already got this alcohol made here. And I'm thinking, you know, when I have an alcohol, I can take its proton off and make an O-. And the Williamson ether synthesis should always be in the back of your mind for a synthesis of an ether. That's a great option. All I need this carbon, I need A, a carbon to be here, and B, the carbon to have a leaving group on it. Why don't we just put a carbon on there first? Because I know if I put just a methyl there, it's called benzylic, and it's pretty easy to put halogens on a benzylic position. I think I've got my answer. I'm going to put a methyl on there first, and then use my friend NBS. Now, careful, methyl is a carbon group, so you can't just say, here's my carbon group. You got to tell me where you got it from. And that's pretty straightforward, isn't it? CH3OH is your alcohol that you're allowed to start with. And if you hit it up with some SOCl2 and pyridine, you're there. And you've got CH3Cl. And now you're going to methylate the para position of our molecule. Got an iodine on top. CH2, CH2R here. Nice methyl here. I'm going to put a bromine on that. Oh, see, now I would lose some points. I just realized something. There's a flaw in my strategy. Sometimes it's test day. I'm going to just take my lumps here. Yep, Dr. Whitaker's going to come back and say, well, I'm only going to give you half credit here because not only are you going to brominate there, benzylic, but you're going to brominate here, and there's a really good chance you're going to get more bromine here than here because it's more substituted. So there was a slight flaw in my logic. I mean, I can give you a verbal correction. Oh, I touched something I shouldn't have. Computer doesn't like my flawed logic. There's a bromine here. We would have also got some bromine down here. I'll pretend I didn't know that. Maybe the teacher will miss it. Yeah, you'd get some bromine there. Finishing up. We're going to take our, why don't we do it this way? I know we don't like yellow arrows because they don't show up very well, but that's a reason why I can use it right here. I'm going to hit that molecule with KH and put it right over the arrow here. And then when I mix these two, I'm going to put in a little DMSO to sweeten the yield. Because it's an SN2 reaction. You don't have to put a solvent there. I do not mind. But you can actually use our short form here for target and be done with that. And the rest is pretending it was a retrosynthetic analysis all the way along. We'll go with a color that sticks out a little bit. Hot pink. That came from this. And this came from this. And this came from this. Which came from this. It's very therapeutic. Which came from that. And that came from here. And this came from D-ribose. And this came from furfural. That's the name of the aldehyde. And that came from benzyl alcohol, or a benzyl-ish alcohol. Yeah, this is a lot of work. And where are we at now? This came from here. And this came from here. And I think that covers this whole retro problem. I think I'm going to do a short segment that will overcome the issue here. So after I close this out, I'm going to copy paste this chunk here where I lost some points with this allylic bromination because, I got some ideas. And I'll see you shortly.